apparently I escaped and there's one left. There's bugs in my code. But I won! We'll pretend that that other zombie doesn't exist. Hello again. So, in this video, we're not going to look at the hardware that I've been playing with the RC2014. We're actually going to look at writing some code for it. I found this fantastic old book. I think I found it in a charity shop or something. You can tell it's old because it was made by W.H. Smith, back when W.H. Smith actually had decent books that were worth reading and weren't just the post office. So this is one of those multi-platform books full of basic code listings. You know, it's for the Spectrum and the Electron and VIC-20. Doesn't mention the RC2014, and it certainly doesn't mention Z80 assembly language. But whilst rooting through it, I came across a game, and it's a fantastic game. So what I've done is I've converted this basic game into Z80, and let's have a play. Right then, so this is Zombies. It's a turn-based strategy game. You've got to survive, well, survive long enough, possibly. I think you die of boredom or starvation before anything else, but anyway, got to survive by luring zombies into the quicksand. The zombies will move in straight lines towards you. They'll eat you, and if you fall in the quicksand or the swamp, you drown. This is a nice test of the joystick module that I built and of the RC2014 in general, but mostly it was complicated enough to actually teach me some Z80. I had a lot of fun figuring out how to write this code. The game isn't that exciting, but figuring out the code really was quite exciting and fun. So here we go, let's have a play. The @ sign on the screen, that thing, is me. The Z's are zombies. Everything else that's not green is going to kill me. You'll notice that nothing's happening. That is by design. This is one of those thoughtful games. A cunning way of masking the fact that your computer probably runs at 1 or 2 megahertz and isn't really capable of doing much else, and that all it can do is print text on the screen. I need to make it so that I can lower those red Z's into the blue and yellow % signs. But if I just start moving around, you can see the Z's start to home in on me. And I die, and I was eaten by a zombie. So, let's have another go. Yep, I'm screwed from the beginning, because there's no way out of this situation. And if I move up, they're just going to home in on me. Yep, dead. So, ooh, this one might be winnable. Oh, you see, we get weird stuff like this. This is where my serial connection has gone a bit mad, and it's dropped a character. So, things have gone a bit screwy. Oh, I'm dead again. Look, there I am. I need to run away from the zombies. Help me, help me. Oh, I'm dead. Okay, we'll try again. Let's see if we can lower them into the quicksand. So sometimes staying still is the key to playing this. And if we go up, and boom. Hey, I won. There we are. So there's a bit more to this game. I mean, in this situation, you're screwed. You're just not going to win. You may as well yeet yourself off into the swamps. Here, possibly win it, maybe. Nope, dead. You see, you need a decent amount of swamp between you and the zombies. And if you get them in a line like this, you can win every time. The logic for working out the position, yeah, I'm dead instantly, look at that. Drink. Yep, so dead, it drew random gibberish on the screen. Right, so I'm trying to convert a basic game into Z80 assembly because I like a challenge, and this is certainly going to be one. So the first thing I'll need to do is understand this basic code, and then figure out how the logic works. I could just play the game, and then, you know, play it, and figure out the rules from that, but I think it'd be more fun to actually look at the code. So what I did was, I had to scan it in, and then print it off, so that I could then write all over it. And here we go. This is the entire code for the game. The people that wrote this book are quite clever. It's certainly going to be a game of fun, definitely. The code there doesn't look like much, does it? It's one page and a tiny little column. What they're not showing you is that there's another page full of extra routines that you have to type in, and they're all customized for depending on which ancient computer you're using. If you pay a bit more attention to the code, You'll also notice it's really packed together. All the variables are single letters, there's no comments in anything, it's got multiple pieces of code on the same line, some of the lines wrap several times, there's a lot of go subs and go tos to like random numbers. It took a fair amount of figuring out to work out the general logic of this code. If you look, it starts off by printing an amazing title screen, and then there's these weird go subs that I figured out were just like a delay and then a clearing of the screen. This bit here actually prints out the game screen. Then we've got two arrays for where the zombies and the quicksand are, and they're 2 item arrays, so it just stores the X and Y position. Then there's a bit of farting around to work out some positions for all these initial items. It's just using some random number generation. This is not neatly structured code in the slightest. If you're used to something like Python, where it's all neatly lined up, or C, where you can write it like this if you want to, but no one does, then this is probably going to give you some nightmares. Like, there's a for loop that starts just here, and then it stops here. It doesn't start at the beginning of the line, no. It starts a bit inwards because they've shoved a variable in to begin the start of that line to make it fit better. I typed all this out and it took far too long. You know, there's like semicolon and then a colon, and if you get that wrong, the game doesn't work. Fortunately, and it's quite rare with these books that they've bothered to do this, they've actually explained what all this code does in sections. And that was really helpful for figuring all this code out. It is one of those rare games in these books that's interactive. You can actually play it as a game and move a character around the screen. It's not something where you type numbers in and it just gives you some more numbers back. A lot of these basic games from back in the day were just like that. You'd have no actual gameplay. As you can see, I've written all over it to try and figure out what all this stuff means, try and work out what these Z's are, like what's 35 mean, what's at line 2400, this random bit of code here that is seemingly a bit odd, but we'll come on to that in a minute. It's actually quite clever. So this is what we're trying to convert into Z80 assembly so I can run it on my RC2014. I'm mostly doing this for the experience of learning how to write assembly rather than having a fun game to play at the end. If I have a game that's moderately entertaining for at least 30 seconds, I'm considering that a win. So let's set the scene of this game then. According to this nice little fancy introduction that they probably spent far too long thinking about, you've been abandoned at a lost Amazonian ranch from some count for some reason. He's a big game hunter. Okay, so you've been set free and you've got half a day's head start. And then there's 4 zombies, because of course in the Amazon there's going to be zombies. Why not? There could be lions, there could be tigers. But no, there's zombies. The ranch is surrounded on all sides by impenetrable swamp, so you can't escape. So already you're a bit screwed. And you're being chased by zombies. The 80s had fantastic ideas for games, and then it all just went a bit sideways. This has gone so sideways, I think it's come back round on itself. Now, for all its slightly bizarre premise and gameplay ideas, looking through this code you find some interesting little routines and ways that they've solved certain problems. Like in this game, you've got to be able to move the character, so they've decided you should have an 8-way character movement. So they've decided the numbers 1 to 9 will move you around the screen. Now, if you look at this little grid, it looks kind of sensible, doesn't it? You might be thinking that it looks a bit like a PC keypad. So let's have a look at one of those. But if you'll notice, it's upside down. So maybe they were thinking of calculator keypads, which were that way up. But no, computers didn't have those on them either. So what they've got is some quite clever logic, and it took me a while to figure this stuff out. This is the kind of gibberish you get in BASIC. There's something clever, but then there's no explanation of what it does or how it does it. And you've just got to sit and figure it out. What this does is it converts this 1 to 9 into a positive or negative number. It'll either give you -1, 0, or 1. And then through the maths, it'll calculate how much to add on to your current position to make you move. As an example, all this is done using integers. Okay, if you try this on a calculator, it won't work. But if you do it using integer maths, it works perfectly. So suppose I want to move diagonally up and to the right. Now, on a screen, 0, 0 is in the top left corner. So I want to take 1 off my Y position, and I want to add 1 to my X position. So if I press 3, 3 minus 4 divided by 3 in integers is -1. All this maths gives me 1. So then if I add C, which is 1, to my current position, I'm going to move across by 1. And if I add -1 to my current position, that's the same as taking 1 off, I move up. If you try it with other numbers, it works as well. If you put 9 into it, D comes out as 1 and C comes out as 1. If you put 1 into it, D comes out as -1 and C comes out as -1. It's quite a clever little routine. I was going to use this, but then realised it's completely pointless and irrelevant to what I'm writing. But it was quite fun working this out. I had a nice little moment where I figured out exactly what this code was doing. If you've seen other videos that I've made on the RC2014, or you've got one yourself, you'll have realised that it's all run through a serial terminal. There's no actual video output and there's no actual keyboard input. So the graphics, as it were, on this game are just single letters of the alphabet. Anything you can type on the keyboard, that's what we're printing on the screen. There's not even any of those extended ASCII characters that you found on the PC that could be made to look like shapes. So there's got to be a way of somehow printing on the screen at positions where things need to go. If I need the player at position 1010, I somehow need to tell the terminal to put the character there. Now, fortunately, that's been thought of because we've already got ANSI escape sequences, which is a whole thing that I'm not going to go into. All you need to know is that the terminal is somewhat clever. If it receives a certain string of characters that start with a certain escape code, it'll understand that to mean something to do rather than something to print on the screen. So what we've got is the escape code. That makes the terminal pay attention to the next characters coming up. Then we've got, this is supposed to be intensity. 1 is supposed to be bright, 2 is supposed to be dim. Then we've got the foreground and background colours, and there's a little table that I found on the internet of what these colours mean. And then you've got the text, and you've got the carriage return line feed. If you send that string of characters to the terminal, it'll understand that as meaning print those words in red on black at bright intensity. Print these words in, I think it's blue on black at bright intensity. So you can at least make things look nice. When you start programming at such a low level, there's a lot of things that normally you take for granted that don't happen. Usually, if you've got some sort of game controller, like an Xbox gamepad, and you're programming in something like Unity, if you press an up button, you will receive one single up button notification. On something as simple as what I've got, there's none of that. There is literally just bits appearing on the data bus, and as I read them, I capture them at whatever state they're in. So, here's the code. So what we're trying to do is work out whether you've pressed the stick and you've released it, and not that you're holding it down and trying to move in multiple goes across the screen. This is not an interactive game like that. You've got to press the stick once and then let go. You're supposed to, between each go, look at the screen and plan your next move very carefully. Remember, you're supposed to be chased by zombies. You're not just going to run around in a panic. You'll get eaten instantly, which this game kind of simulates. If you think about it and move step by step and think, you last a bit longer. So what we do is we trap you in this loop where I keep repeatedly reading in the joystick and trying to work out whether it's the first time you've pressed it since you let go. To do that, I need a variable called stick pressed, which either holds a 1 or a 0. If stick pressed is 1, it means you've held down the stick. If it's 0, it means you've let go. So then I can use that to work out that if currently you're pressing the stick, but previously you weren't, we can continue with the code. But if you're currently pressing the stick and previously you were pressing the stick, then you go back up to the top and I read the joystick again. And you get trapped in that loop until you've let go of the stick. Because it might be that you've actually pressed up and let go of it, but because you held it up for multiple CPU cycles, this is whizzing away at a whole 10 megahertz. So unless you can flick the stick incredibly quickly, and the internals of the joystick don't bounce around either, it's going to read this multiple times. I need a way of filtering all that out. And that's what this is trying to do. Once we've got some nice valid clean input, we need to work out which button it was that you pressed. We need to react to your input. And this is where we get a lot of register twiddling. This is Z80 assembly all over. You can do a lot, providing you break it down into its minute individual single steps. This is what assembly programming is like. I restore the direction that you've pressed. I AND it with 1, because up means 1. I then compare A with 1, to check that there is 1. If it isn't, I then go off and do another one. Otherwise, I load the current Y position into A, I take one off it, and then I put the current Y position back where it came from. You're explaining to a machine step by step what to do. It can't do these things at once. In Python, this would just be an if statement. You'd have something that says, if input equals 1, then take 1 off the Y position. Now, these zombies have some, what they loosely term AI. It's really not very clever. Neither's my code. It's quite a good match. All it tries to do is work out how to do a direct path towards the player. So if you've ever done any basic vector arithmetic, that's all it's doing. It's calculating a direction towards the player. To do that though, you need to know whether some numbers match or not. So here's a nice little diagram. Inside the CPU are some status registers. They can tell you whether the last operation you did involved a carry and some other bits and pieces. I'm trying to compare where I am and where the zombie is. So you take one of its Y coordinate and you take one from the other. We either need to know that if they're both the same, then it's possible that either you stood on the player or that you're on the same column or row. If they're not the same, well then we need to know if it's smaller than or greater than, because you're either one side or the other of the player. You need to know which side so you know which way to move. So this is a general gist of what we do. So we have a loop and it runs 4 times, one for each zombie. I've got an array of all the zombie data. It's their X, their Y, and a flag to say if they're dead. So first we load in their XY position, and we load in whether they're dead. If they are dead, we discuss the next one. Otherwise, we now do this bit. And this is that idea that I was saying before. So we get the player's position, we first pick out the X position. We compare it to the X position of the zombie. If the 0 flag is set, so that means the two numbers are equal, then they're on the same X column and I go off and do something about it. If the carry set flag is set, that means they're less than the player's position. That means we need to move backwards, and if the carry flag is not set, it means they're in front. So we need to move forwards along the X position. Here's an overview of the code, and you can see I've split it into multiple files to preserve my sanity. This is the main file. It was getting a bit big, so I had to chop it up into separate files, otherwise I was just going to lose the plot. There, and then there's another one, and some more. So I've got utilities. These are things that I've either found off the internet, or that I've written myself. It's quite nice coding in Z80 actually, because if you want to know how to do random numbers, somebody has written a routine for you. If you want to know how to divide numbers, because nope, it can't do that, you've actually got to manually code it, then someone else has written a routine as well. It's awesome. There's so much documentation out there, it's really quite good to find things. I even found a nice plugin for Visual Studio that prints out information about what opcodes do. So here's a bit to do with printing out ANSI escape sequences. The RC2014's ROM has got a built-in print routine which I've been using, but what I didn't realise is it mangles one of the registers. That caused me about half a day's worth of bug finding, but then I learned quite a lot, which was nice. So here's the main file. First we initialise the game, and all we're doing is we're resetting a bunch of variables to either 0 or to 4 for how many zombies there are. We then clear the screen, show the titles until you press the fire button, clear the screen again. We draw it once because this is ANSI text, we don't have to keep refreshing the screen every game loop. We then generate some positions where the zombies go, same for the quicksand and the player, and then there's this main loop. And all it does, well, not all, but whatever, we get the joystick, we check if the player has fallen in the swamp, or touched a zombie, or touched some quicksand, then we draw them. Then it's the zombies' turn to move, and collisions for the zombies. Then we update the player's position, and we check if the game is over. And there's a bit of debounce logic here, so that if the game is over it doesn't whiz right back round and play itself again, you can actually read the screen. Drawing the screen just prints some of that ASCII text on the screen, this kind of stuff. generating the quicksand creates a random number, masks off the bottom half of it, adds on 3 because otherwise I was finding zombies and things would spawn in the swamp, which was pointless. Then I've got an array of variables. Well, they're not really variables, are they? There's no variables in this. This is just memory locations, I suppose. So they're not even paired up like this. That's just visually to help me understand what's going on. So I've got numbers for where the quicksand goes. These numbers here were just me testing it at one point because I got the X and Y coordinates upside down and got very confused with collision detection. I've then got position of where the player currently is and where they're going to move to. I've got some flags to decide what they've collided with, and a flag to decide whether it's game over. At the bottom is where I include all the other code, and that's completely opposite to every other language, isn't it? In C or Python you include the code you're going to use before you use it. In assembly, the assembler lumps all this stuff together into one binary file. If I include this at the start of the code, then my start point will not be where I think it is. This instruction here is at this memory location. If I include something above it, that instruction will be where that memory location is. And this will be somewhere else, and I won't know where it is. So you include things at the bottom. It's just like I create what we'd call a variable at the end of my code and not at the front, because the assembler turns all these into memory locations. The computer doesn't ever see these. This is the hex dump that I load into the computer. Right, so here's how I build this code, because I've got myself quite a nice little setup going here. So I've got Visual Studio, and I write my code, and then I save it. This is all inside a Windows subsystem for Linux Debian installation. And then I'm using PowerShell with 2 tabs. One of them is running Minicom inside Linux to talk to the RC2014. The other one is my shell. And inside here, I've got various bits of junk that I've been playing with. There's some of the previous videos code in here. There's a build script. There's the assembler. And all I do is I build the code. I then nip back into here. I get the hex file. I select all of it and copy it. I go into Minicom. I make sure I've rebooted the machine, otherwise it sometimes gets very confused. And then I paste it. And if it said that, the code is in. And then I can just run it. And there we go. That's how easy developing this stuff is. There's no messing around with memory cards or uploading things and waiting for it to burn to an EEPROM. I just paste it into a terminal and the monitor understands what to do with it. It's really nice. So there we go. That's my little adventure in challenging myself to write an actual full working game using Z80 assembler. And it was really good. I didn't really know much before I started this. I knew enough to poke things into memory and pull them back out and twiddle around with them in registers. But to do any sort of meaningful output that was a bit more than adding numbers together, I didn't know how to do. And I learnt so much doing this. So I'd definitely recommend that if you're even vaguely interested in assembly language, you give it a go. You don't even need a computer to do this. You could just get your favourite old 8-bit computer as an emulator and then just start learning. You know, you could get an Apple II emulator that's got a built-in monitor and just start poking around with it. You could get an old C64 or Commodore PET emulator and play with that too, or a Spectrum. It doesn't really matter. There's so much documentation about this now because it's been out there for 40 years. You can very quickly figure stuff out that back in the day, without the internet, you'd have had to have first known that this book existed, and then gone and bought it, or borrowed it from the library. And if the book didn't make any sense to you, you were either stuck or you needed to find someone that knew what they were doing, and it just took so long to learn things. But now you can just Google it, and it's there, and there'll be someone else who's done a very similar thing. So I hope you found that interesting. If you want to play this game on your machine, or you've got some of the Z80 machine that talks over serial, it should work with that too, there's nothing special in this code, then I'll put a link to a GitHub repository with it on. But thank you for watching, and if you've not clicked the subscribe button, click that because I'm going to keep making more videos. So I'll see you next time. Goodbye.